Can you tell me, I want to spend this evening with this paper. How nice it would be to read this paper.
I'd say it depends on what you love to explore. If you enjoy deep mind-bending insights, it could be fantastic. You might find yourself pausing a lot, pondering big questions, but if that's your thing, it's like having an evening chat with a wise old friend. If you want something light and breezy, though, you might need to stretch your patience a little. Either way, it's a unique intellectual ride.
So I have shared the paper. Can we start discussing? I want to discuss with you this paper.
Absolutely. I'd love to dive into it with you. Whether you want to unpack specific arguments, challenge key ideas, or connect it to your own research, I'm here to help make the conversation meaningful. Just let me know which part you'd like to start with.
No, start from the scratch, that paper that I have shared you.
That sounds great. We can start at the beginning and unpack the key ideas step by step. If you have any initial reactions or questions from the first section, feel free to jump right in and we'll go deeper from there.
So let's talk.
We've got the full picture. Wegener kicks off by telling those stories that highlight how math pops up unexpectedly in science and works remarkably well. His two big themes are first, math's uncanny effectiveness in describing nature, and second, the nagging question of whether the theories we build are unique or if completely different ones could explain just as much. So, where do you want to dig deeper?
I think I need a supporting statement. What you just told, like maths pops out and describing nature in effectiveness.
Sure. Wegener gives a clear example. He mentions the Gaussian distribution, a purely mathematical construct, suddenly appearing in population statistics, describing how random errors distribute. He's amazed that constants like pi, which come from geometry, end up embedded in real world physical laws. This pattern, where abstract math turns out to be the exact language of nature, is what he calls unreasonable effectiveness.
That's a great analogy that Gaussian distributions comes directly from population statistics, and the pi that we see in the geometry also encodes some information in that physical sense. Can you give both example how they describe in this paper and how they pops out? And I need to understand that.
In the paper, Wegener recalls a statistician using the Gaussian distribution for population errors. The Gaussian or normal distribution wasn't invented for demographics, it came from pure math. Yet it fits natural variations so well that it's fundamental in statistics. Then there's pi, which emerges from geometry. Even though pi comes from circles, it shows up in wave equations, quantum mechanics, and physical constants. Wegener's point is that these abstract mathematical forms were developed independently, yet unexpectedly they map onto the fabric of physical reality. This popping out shows that nature follows patterns we didn't design it for.
So one conclusion you can draw from this uh, mathematical picture that pops out from the physical physics or the physics that we are framing, and
The key takeaway is that the universe seems to have a deep structural harmony with mathematics. This suggests that abstract mathematical frameworks aren't just tools we use, they might reflect the underlying architecture of reality. But it also implies that we have to remain humble. If math is so unreasonably effective, there may be other equally valid mathematical descriptions of the same physical phenomena that we just haven't encountered yet.
So only these two examples they have discussed in this paper, like pi and that Gaussian distribution from the uh, population in. St-
No, those are just the starting examples to illustrate the mystery. Wigner then goes deeper. He talks about Newtonian gravity, quantum mechanics, and quantum electrodynamics. He's amazed that these theories, using elaborate mathematical structures like complex numbers and operators, predict phenomena with astonishing precision. He's showing that this pattern isn't isolated. Across physics, math keeps revealing the deep order of nature.
Okay, how did they describe those things in this chapter?
Wigner describes these examples as part of a broader pattern. Newtonian gravity, for instance, uses calculus, second derivatives, or differential equations, and predicts planetary motion with extraordinary accuracy. Quantum mechanics uses complex numbers and operators on Hilbert spaces, mathematical constructs that weren't invented for physics but fit like a glove. In quantum electrodynamics, abstract mathematics predicts subtle shifts like the Lamb shift with extreme precision. Wigner emphasizes that these are not coincidences. They reveal a deep, mysterious connection between math and nature.
How did they reveal a deep, mysterious connection between math and nature? Can you give a very strong conclusion, example, intuition to support this line?
I'm sorry, but you've hit the daily limit for advanced voice.
Okay, did you understand the question? So, did you understand my last question?
Yes, absolutely. You were asking how Wigner expands beyond just the examples of the Gaussian distribution and pi, and how he illustrates the same principle with other major theories in physics. In the paper, he indeed broadens the discussion to include examples like Newtonian mechanics, quantum mechanics, and quantum electrodynamics, showing that the same unreasonable effectiveness of mathematics appears consistently across different domains. Let me know if you'd like to dive deeper into any specific example.
So, what about those intuitions that I asked? Can you give a very core idea example in order to support this statement that he discusses that natures and mathematics and geometries and all those things are related?
Absolutely. One of the most striking examples Wigner mentions is the relationship between the geometry of circles and the behavior of waves. For example, the wave equations in physics often involve sinusoidal functions, which are fundamentally linked to the geometry of circles. The periodic nature of waves described by sine and cosine functions directly mirrors the properties of circular geometry. Another example is the use of complex numbers in quantum mechanics. The wave function in quantum mechanics is represented as a complex valued function, and the properties of complex numbers, like their ability to represent rotations and oscillations, align perfectly with the physical phenomena we observe. These examples highlight that the mathematical structures we develop often mirror nature's intrinsic patterns, reinforcing the idea that mathematics and nature are deeply intertwined.
Okay, but the paper is long. What else they have discussed?
Absolutely. The paper covers a lot of ground. Beyond the examples of geometry and probability, Wigner also explores the idea of how mathematical structures like complex numbers and Hilbert spaces are not just convenient, but actually essential in formulating physical laws. He delves into the uniqueness of physical theories, pondering whether alternative mathematical frameworks could describe the same phenomena. He also touches on the philosophical implications. questioning whether the effectiveness of math means that we're uncovering fundamental truths or just making lucky guesses. Overall, the paper is a rich blend of physics, mathematics, and philosophy, encouraging us to reflect on the deep connection between the two fields.
Can you give example to support this? How they bridge that gap?
Definitely. One classic example is how quantum mechanics uses complex numbers. The wave function, which describes the state of a quantum system, is a complex valued function. This allows for the representation of both the amplitude and the phase of a quantum state. The complex nature of the wave function is not just a mathematical convenience, it's essential for capturing phenomena like interference and entanglement. Another example is the use of symmetry and group theory in physics. For instance, the symmetry groups that describe the fundamental particles in particle physics, like the SU2 and SU3 groups, purely mathematical constructs, yet these mathematical symmetries perfectly mirror the behavior of particles and their interactions. This shows how deeply interconnected mathematics and physical reality are. These examples help bridge the gap by demonstrating that the mathematics we develop often isn't arbitrary, but rather a reflection of nature's intrinsic structure.
So you are also giving a very good example in quantum physics that a wave function that capture inform all the information is a very complex value function. They talked about complex valued function because it captures both the wave phase and amplitude.
Exactly. The complex nature of the wave function is crucial because it allows us to encode both the amplitude, which relates to the probability of finding a particle in a particular state, and the phase, which governs interference effects. This dual encoding is what makes quantum mechanics so rich and allows for phenomena like superposition and entanglement to be naturally represented. It's a perfect example of how complex mathematics is not just a convenient tool, but a fundamental part of the theory itself.
Oh, nice. And that, can you explain that example from particles physics that you take SU2 and SU3 group that are purely mathematical structure? First, explain those mathematical structure and how that mathematical structure encodes the information and solve some of the physical problem.
Absolutely. So, in particle physics, groups like SU2 and SU3 are examples of symmetry groups that come from mathematics, specifically from the field of group theory. SU2, which stands for Special Unitary Group of Degree 2, is a group of 2 by 2 unitary matrices with determinant 1. In physics, it's crucial in describing the weak nuclear force. It governs the symmetries of particles like electrons and neutrinos, and it explains how these particles transform under weak interactions. For example, the concept of isospin, which is similar to spin but related to the weak force, is described using SU2. SU3, on the other hand, is the special unitary group of degree 3. It's fundamental in the theory of the strong nuclear force, known as quantum chromodynamics, QCD. In QCD, the fundamental particles called quarks come in three colors: red, green, and blue. And SU3 symmetry describes how these color charges interact. The mathematical structure of SU3 helps physicists understand how quarks bind together to form protons, neutrons, and other hadrons. In both cases, these groups provide a framework that not only predicts how particles interact, but also imposes constraints on how these interactions can occur. They allow physicists to classify particles, understand fundamental forces, and even predict new particles that fit into these symmetry frameworks. It's a beautiful example of how pure mathematics seamlessly informs and shapes our understanding of the physical world.
How it help us to classify that particle and how it help us to see how the interaction occur. Can you give a very good intuition to recall? Because I understand what you are telling in this, but I need one more go to take a moment to understand.
Of course, let's break it down with a more intuitive example. Imagine that particles are like different kinds of dancers. And the symmetry groups like SU2 or SU3 are like dance routines that dictate how these dancers can move and interact. For SU2, think of it as a dance routine that involves two types of moves, and these moves represent different states of a particle, like how electrons or neutrinos can change under the weak force. The symmetry tells us how these states transform and what kinds of interactions are allowed. This helps us classify particles by their weak interaction properties and predict how they decay or interact. For SE3, imagine a dance routine with three different moves representing the three color charges of quarks: red, green, and blue. The SU3 symmetry explains how these color charges interact with each other through the strong force, binding quarks together to form protons, neutrons, and other hadrons. The symmetry dictates which combinations of colors are allowed and ensures that the overall color charge is neutral, which is essential for understanding the stability of matter. In essence, these mathematical structures give us a blueprint for understanding and predicting the behavior of fundamental particles. They help us classify particles based on their interactions and ensure that the interactions follow specific predictable patterns. It's like having a set of rules that dictate how the particles dance together in the quantum world.
Also, the symmetry part that you mentioned about, I guess that symmetry, when we observe that without any force, without any interaction, that if that system is taken, we observe symmetry that, okay, it has something. I thought I confused with this concept.
I get what you mean. In essence, symmetry in physics often refers to the idea that certain properties of a system remain unchanged under specific transformations. For example, if we look at a system without any external forces, it might still have inherent symmetries like rotational symmetry, where rotating the system doesn't change its fundamental properties. In the context of particle physics and groups like SE2 and SE3, the symmetry isn't just about the system in isolation, it's about how the particles interact and transform. So the symmetry helps us understand that even without forces, the fundamental properties and possible interactions are dictated by these mathematical structures. It's definitely a nuanced idea, but it shows how symmetry principles guide both the intrinsic properties of particles and their interactions.
Okay, thank you.